Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Welcome to our online lecture series on electrical machines. This is Muhammad Owais, your course instructor from DHA Suffa University. As you are all aware that we are not able to take classes in university, so this alternate arrangement has been made for you guys. So before we start our lectures, let me give you an introduction to how the course is going to be managed. So the weekly schedule shall be as per the details. So we are going to have three recorded video lectures, and this is the very first of these lectures. And these lectures will be updated on LMS weekly on weekly basis. And apart from that, we shall have one interactive Q&A sessions, and it shall be on Friday, every Friday at 3 p.m. PST. We shall be taking these online sessions on Zoom as discussed previously. So for the interactive session, I would like to give you some guidelines. The very first point is that you must first have gone through the recorded video lectures and you have tried to understand the concept which have been discussed in those lectures. If you face problems, the book is with you. Uh, you can have a look from the book as well. And still, if you feel that there are problems, an interactive session has been arranged. But I strongly recommend you that you post your queries to me via email on my official email address, which has been shared here. So this is my official email address, and make sure that you have posted your queries latest by 11 p.m. every Thursday. So since we shall have limited time during the interactive session, therefore I strongly recommend you to post the queries because the first preference shall be given to those queries which have been posted via email. And if we get some time left after those queries, maybe we can take your question live as well. So these are some of the references which shall be used for lecture delivery of this course. The textbook for this course is Electric Machinery Fundamentals by Stephen J. Chapman, 4th edition, and this book has been uploaded on LMS. Apart from that, we shall be using the other books as well, which have been cited in the previous slide. Before starting our new topic, you would remember this. I assigned you some tasks during the first 2 weeks. The task for second week can be seen on this slide. So you were supposed to read and understand topic 1.9 from Chapman. So I hope you are done with this and you now have the understanding of real, reactive and apparent power in AC circuits. If you still haven't gone through this topic, please go through this. Otherwise, you might face problem during the course. In case of queries, you can text me or you can write me an email or you can join us during the interactive session. I also assigned you a task to go through the online lectures of the course Motors and Motor Control Circuits. This course is available on Coursera, and you were supposed to understand the topics which were covered from Module 1 to Module 4. So I hope you have gone through this. The following topics were actually covered during the first 4 weeks. And if you, as you can see, it's more focused towards motors, AC and DC motors. And I hope you now have some idea about AC and DC motors. Now we shall study about AC and DC motors, but students, if you remember, transformer was the topic which we were continuing before proceeding on to leaves. So let's start from where we left. So students, I think it's worth spending some time on the previous topics which we covered in our classes. So before starting anything new, let's discuss some of the previous concepts. Acha ji, the very first topic then is ideal single phase transformer. This was the topic which we previously discussed in our classes. So we said that a single phase transformer is a lossless device, so there are no losses, and we previously discussed the type of losses that are present in a transformer. So the windings have no resistance, which means there are no copper losses. The core is lossless, which means uh, coal losses are not there, or iron losses are not there, and there is no magnetic field surrounding the iron core, which essentially means that all of the flux in the primary gets linked with the secondary. So, and there is no leakage flux at all, and the permeability of the core is assumed to be infinite. So now we are aware about the current and voltage relationship between the primary side and the secondary side of a transformer. But are we able to tell the polarity of the secondary side if we are aware about the polarity of a specific side of the primary winding? So if you know that, for instance, the voltage is positive at let's say at this end, how can you tell at what end the voltage of the secondary will be positive? So we are talking about the polarity of the voltage at the secondary of the transformer. So for that we have the transformer's dot convention, and this is actually used for finding the polarity of the voltage and the direction of the current in transformer windings. So the relationship is as follows. So for finding out the voltage polarity, so if the primary voltage is positive at the dotted end, so you see this is the schematic symbol of an ideal transformer. A transformer has been shown here. So if you see dots here, so two dots have been shown here. So we are trying to figure out what these mean. So let's go ahead again. So if the primary voltage is positive at the dotted end of the winding with respect to the undotted end, so you can see this is positive here. So dotted end is positive. Then the secondary voltage will be positive at the dotted end also. Now, since the dotted end on the secondary is here, the dot is here, so obviously it has to be positive here again. So it says that the primary voltage is if the primary voltage is positive at the dotted end, then the secondary voltage will also be positive at the dotted end. So if this dot had been here, then we had to show this side of the secondary as positive. So polarities have to be assigned accordingly. Now what about the current direction? And it says if the primary current of the transformer flows into the dotted end of the primary winding, so you see here the current is entering into the dotted end, then the secondary current will flow out of the dotted end of the secondary winding. So you can see here, so that since the dot is here, so therefore now the current will actually be flowing out of this dotted end. Okay, students, now this is what transformer dot convention is about. So continuing with the revision of our previous topics, we discussed this relationship for the input power of an ideal transformer. So it's given by Vp into Ip cos theta p, where theta p is at the angle between the primary voltage and the primary current. In this relation, using the very same relation, we can write down the relation for the output power of an ideal transformer. And please remember that for an ideal transformer, the two angles or the thetas are same, essentially, which means for an ideal transformer, the power factor at the primary and secondary is exactly the same. So let me relate the output power with the input power using the relations. These are the relations which have been discussed previously, and this A is nothing but the turns ratio, and this is defined as Vp over Vs as per the convention of Chapman. So in other books, this A or this turns ratio may be defined the other way around as Vs or Vp, but we shall remain consistent. We shall be using this relation as Vp divided by Vs. So now what I'm going to do is I'm going to somehow replace this Vs in terms of Vp using this very relation, and Is will be again replaced by another relation in terms of Ip using the relation given here. So let's do this. Once we do this, this is the output power. Again, you see the output power is now this term A and A. What happens that these two cancel out each other, and you find out that the output power is nothing but equal to the input power. Yeah, so the output power and the input power are exactly the same for an ideal transformer, and it does make sense. Okay, so the same relation applies to the reactive power Q and the apparent power S as well. I strongly recommend you to please remember these relations. These are very basic, particularly for the apparent power. We shall be using these relations shortly, maybe in this lecture or in the next lecture after this one. Now let's discuss how an impedance is transformed across a transformer. We have studied and we now are aware that a transformer changes voltages and current levels. So then it also changes the ratio between the voltage and current, and hence the apparent impedance of an element. So how do you define the impedance of a device or an element? So we define it as the ratio. It defines as the ratio of the phasor voltage across it to the phasor current flowing through it, as you can see here shown in the figure. Okay. Now, if the secondary current is called IS, let me call it IS, and the secondary voltage be V of S, then the impedance of this load is given by ZL. And how do we define this impedance? It's as Vs over Is. Okay. Now, what about the apparent impedance of the primary circuit of the transformer? Is given by ZL dash as Vp over Ip. So it's the prime voltage at the primary divided by the current flowing through the primary. So now we want to see how the two impedances are related with each other. So, or if I want to transform the impedance from maybe from secondary to the primary of the transformer, how are these related with each other, or how can we transform those impedances? So in the previous slide, we said that impedance is given by at the primary side is given by Vp or Ip. ZL dash has been defined as the impedance of the primary circuit. So, but we know how the primary voltages and secondary voltages are related in terms of the turn ratio. This is again the same relation. Vp is equal to AVS and Ip is equal to Is over A. So students, try to understand what I'm trying to do here. What I am trying is to relate the impedance, the two impedances, the secondary and the primary impedance, so that if we need to transform one of the impedance to the other side of the transformer, we can do so. Okay, if you put these two relations, this Vp and Ip into this equation, what do you get? It's pretty straightforward. So what happens is this relation. You get ZL dash is given by A square into Vs over Is. And now this term Vs or Is. So this term I'm talking about, this Vs over Is. This what is this? This is nothing but the impedance at the secondary side, which we define as ZL. So now we have a relation. So we say that the apparent impedance of the primary is equal to A square into the impedance at the secondary side. So this is a very important relation. Whenever if we want to transform an impedance from secondary to primary, this is the relation which we shall be using, or we can use this relation the vice versa of this relation as well. So we can transform from primary to secondary as well. So this was the question which was our last, which we discussed in our last class. I also assign you this as your home task to go through this question. So probably you must have gone through this, but in case you still have confusion, I'm going through this example here. So please focus and see if you still have any problems. So this example actually discusses a single phase power system 480 volt 60 hertz generator. It's here on the input side. We have a generator, and then you have the line impedance of 0.18 plus j 0.24 ohm. This is the impedance of the line, and then you have a load, and the impedance of this load is 4 plus j 3 ohm. So, students, I instructed you to go through topic 1.9 from Chapman so that you get some idea about real, reactive, and apparent power, and how the concepts are related with each other. And it was very important to go through that topic. I'm again urging you, motivating you to go through that topic if you haven't so far. So, yeah, so in part A, we let's see what have been asked. So it says if the power system is exactly as described below, we're talking here, what will the voltage at the load be? So we have to find out the voltage at the load, and also we have to find out the transmission line losses. So actually, here Chapman is giving us an example of a transmission system in which transformers have not been used in part A. So we shall see what is the effect on transmission line losses when we do not use a transformer. Okay, so let's continue with part A. Here we are supposed to find out the load voltage first. This is my load, which is a complex number 4 plus J3 ohm. So we need to find out the load voltage. And voltage is simply given by the product of the current and the impedance. So we have this load current and the load impedance. But for that, I need to find out the load current first. And if you pay attention, this load current and my line current, these are exactly the same since the load is in series with the line. So therefore, line current and load current, and in fact, uh, the generator current, these are all same for this particular scenario. So now we just need to find one of the current, and all the others will also be the same. So how do I find out this line current? For that, I can either apply a KVL maybe, or I can simply find out as given by the voltage, the generated voltage divided by the impedance in the circuit. Now for the impedance, if you have not noticed, there will be two parts to impedance. One is this load impedance, and the other part is going to be my line impedance. And now since these two are in series with each other, so the total impedance is simply the load impedance plus the line impedance, and then we shall be able to get my line current. Let's do it. So this is shown here by just simply putting in the values. We have all the values, all the required values, the voltage at the generator side, the impedances, and once we solve this, we get the value of the line current. Okay, so this minus this is showing that current is actually lagging the voltage, and it does make sense. Acha ji students, now let's find out the load voltage. The load voltage is nothing but the load current and the load impedance. Now since I have my load current, just simply multiply it with the load impedance to get the value of the load voltage. This is how we do so, and the answer is here. This is my load voltage. Now how do I find out the line losses, the transmission line losses? So the transmission line losses are nothing but the I square R losses. So I square R losses, when we are talking about, then we shall be only considering the resistance of the transmission line 0.18, and this is simply uh, find out using the basic relationship of line losses. It says I square into R line. So I line is nothing but the magnitude of the line current, which was 90.8 as we solved in the previous slide, and the resistance in the line is 0.18 ohm. So once you solve this, you get this value of 1484 watts. Now this is significant, but at the moment you may not be able to relate it what I'm talking about. For that we have to solve part B, and then we can compare the two line losses. and we shall see whether there is any effect on the line losses once we use transformers in our transmission line system. And so to understand this, we have part B. Now here, the question says that here we have two transformers. This transformer T1, this is a step-up transformer. So how do I know that this is a step-up transformer? It's pretty straightforward. So you have been given the turns ratio, and you say that you can see that this is a step-up transformer as the number of windings on the secondary sides are larger than the number of windings at the primary side. Whereas the second transformer, the T2, this is a this is a step-down transformer. You guessed it correctly. So now we have two transformers in our transmission system, and we are going to see what happens. So we are now required to find out the load voltage. What is the load voltage and what will be the transmission line losses? Remember, everything is same. The line is same, the load is same, load impedance is same, and so are the values of the generator which we are using. Okay, at the generator, and you can see it's the same value of the voltage. So now we have to see what are the effects of using the transformers. Okay, जी students, I hope so far so good, and you are able to cope up with the stuff which I have discussed with you. So now what we have to do is we have to now deal with two transformers. तो क्या करना चाहिए अब हमें जब हमारे पास दो transformers हैं. So since we are talking about ideal transformer, तो हमें इस वक्त चीज़ें बड़ी आसान है. What we do is हम करेंगे ये कि ट्रांसफार्मर को सिंपली रिप्लेस कर देंगे और अपने सर्किट को किसी एक साइड के ऊपर ले जाएंगे ट्रांसफार्मर के. So either we move every stuff to the primary or to the secondary and then we analyze. उसका फायदा क्या होगा? क्योंकि जब हम एक साइड के ऊपर ले जाएंगे तो हमारे पास जो वोल्टेज एंड करंट के रिलेशनशिप्स होंगे वो इंतहाई आसान हो जाएंगे. ओके क्योंकि the new circuit, as it says, the new circuit will be without a transformer and it can be solved for its voltages and currents using simply Kirchhoff's current law or the voltage laws, जैसे कि हमने पार्ट ए के अंदर डिस्कस किया था. आपको याद है पार्ट ए जो अभी हमने पीछे किया था उसके अंदर हमने ये किया था कि एक ही साइड के ऊपर हमारे पास सर्किट था, कोई ट्रांसफार्मर नहीं था, हमने सिंपली केसीएल अप्लाई किया, किरचॉफ्स वोल्टेज लॉ अप्लाई किया और हमने लाइन करंट निकाल लिया था, जिसके बाद हम लोड वोल्टेज भी निकाल चुके थे. सो फॉर दैट व्हाट वी नीड टू डू इज वी नीड टू समहाउ ट्रांसफॉर्म प्राइमरी और टू रेफर वन साइड ऑफ द ट्रांसफार्मर टू द अदर साइड. ओके, ये चीज आपको यहाँ बताई जा रही है. सो हमें उसके लिए यूज करना है क्या चाहिए, हमें उसके लिए ट्रांसफार्मर की टर्न्स रेशियो चाहिए कि किस तरीके से हमने ट्रांसफार्मर को रेफर करना है. So then the turns ratio of the transformer can be used to determine the voltages and currents on the other side of the transformer. देखिए अभी हम करते हैं किस तरीके से इसको. So this process is actually which process I'm referring to, replacing one side of a transformer by its equivalent at the other side's voltage level. क्योंकि आपको मालूम है प्राइमरी और सेकेंडरी डिफरेंट वोल्टेज लेवल के ऊपर है, तो हमें ट्रांसफॉर्म करके सेम वोल्टेज लेवल के ऊपर इनको लेकर आना पड़ेगा. दिस इज नोन एज रेफरिंग द फर्स्ट साइड ऑफ द ट्रांसफॉर्मर टू द सेकंड साइड. सो यही अब हम यहाँ पे करने जा रहे हैं. So the discussion which we had on the previous slide, it may not be very clear to you at this moment, but once you solve this circuit, inshallah everything will be clear to you. As I said in the previous slide, what we need to do is we need to refer one side of the transformer to the other side of the transformer. So the end goal is, or the ultimate goal is to somehow replace transformer by some other relations. Let's see how can this be done. So what we are going to do in this part B is the very first step shall be to eliminate transformer T2. So we are going to eliminate it, and how we are going to do is we are going to refer the load, this load Z load on the secondary, we are going to refer this load to the transmission lines voltage, which means that this voltage or this load will be referred to the primary of transformer T2. Remember students, ये काम हमने चंद शुरू में जब हमने टॉपिक स्टार्ट किया था इस सवाल से पहले, तो हमने ट्रांसफॉर्मेशन की बात की थी कि हाउ टू ट्रांसफॉर्म impedance from one side to the other side. That concept is going to be used here again. Okay, so once we do this, we shall have only one transformer left. Okay, after referring this load to the primary side of the transformer T2. Now we are left with this transformer T1, and again we shall do the same. We shall replace this transformer T1 by simply referring the transmission line elements, everything which we now have at the transmission side. We shall have this line impedance, and we shall also have this load, the referred load at the primary of transformer T2. Now हमें करना ये होगा कि हमें इसको रेफर करना पड़ेगा to the primary side of transformer T1. Once we do this, then this part will exactly become the same as part A. So let's begin with this. Okay, G, now let's begin by eliminating transformer T2. So we have to eliminate transformer T2, and we have to refer the load at the secondary of transformer T2 to the primary side. So if you remember, we discussed the relationship, how the impedances are related with each other. So we said that, if you remember, it was ZL dash was A square into ZL, where this ZL was nothing. ZL dash was the impedance at the primary side of the transformer, and this ZL was the impedance at the secondary of the transformer. And this A is nothing but the turns ratio. Okay, so this A is turns ratio. And how do we find out the turns ratio? It's given here actually in this case. So हम करने ये जा रहे हैं कि we shall be referring the secondary the load at the secondary of transformer T2 to the primary of transformer T1. So let's do this using this very relationship. So now you need to remember these relationship and start utilizing and using these relationship into your circuit. For that, let me rub this out first. Okay, I hope you are comfortable with this and appreciating my skills as well, my artistic skills. So that was just on the lighter part. So now, so ये हमारे पास Z load आ गया. Now this is Z load dash is what? This Z load dash is nothing but this is the load which is at the primary side of the transformer T2 now. It was on the secondary, we have referred it using this very relationship, and this is now equal to 400 plus J300 ohm. So now the transformer T2 has been eliminated. We do not have the transformer T2 anymore. So then the circuit simply becomes this. If you see here, you do not see any transformer T2. It has been replaced by equivalent circuit. Remember, this is an ideal transformer at this moment. We are talking about ideal transformers. So it won't be that easy for real transformers. Then we need to, we shall need to first discuss the equivalent circuit of an ideal transformer. Don't worry about it. We shall be doing it in our next lectures in our upcoming lectures. So now let's get back to this question again. We have this resistance, this impedance, and now the line impedance as well. So now what is on this side of the line? It's simply two impedances, the line impedance and this Z dash load, the referred load to the primary side. Okay. Now these two impedances are again in series with each other. So Z line and Z dash load are in series with each other. If we solve these together, then we shall be able to simply add these up together. So the equivalent impedance is now, yeah, this is it. This is your equivalent impedance, the line impedance plus the impedance of the load which has been referred to the primary side. Okay. So this is not load impedance. Remember, this is the impedance of the load when it has been referred to the primary of transformer T2. And this is what you get. So now you need to know how to convert this rectangular coordinates into this polar coordinates. Okay. So these are the previous concepts of ENA. So please make sure that you have those concepts cleared. In case you still have those queries, maybe we can schedule an extra interactive session for that. Okay, G, now what's next? Now is the time to eliminate transformer T1. Okay, so we know it's not that easy to eliminate transformers, huh? So I hope you are getting what I mean. So I'm not talking about those transformers. This is our electrical transformer. We are trying to eliminate transformer T1. We are done with transformer T2. Now we have to eliminate transformer T1, and again it will be using the same relationship. So we have to see what is at the secondary of the transformer T1. And now we are only left with my line impedance and my load referred load impedance, which we solved, and we got the answer. So now let's continue with this. So now once we now what we do is we have to refer this impedance, this total impedance Z line plus Z load dash, to the primary of transformer T1. So we use again the same relationship. This relationship is A square Z equivalent. Okay, but there is one very important point. There are chances of mistake here. Now this A is different. Okay, so if I say A1 is not equal to A2, okay, so this A1 is not equivalent to A2. Why do I say this? Because transformer T1 was a different transformer, okay, and it was a step up transformer, and transformer T2 was a step down transformer. So the two ratios are not same, even if they appear so. So what you need to do is, for each of the transformer, please find out the turns ratio first. Okay. So here for both transformer, it has been simply written as A. So now here for this transformer, A is nothing but 1 over 10. Okay, so now we have the value of A, and by simply using this relationship, we can find out the impedance, total impedance, which has now been reflected to the primary of the transformer T1, which means that we do not have any transformer with us now. Both the transformers have been eliminated, and we are now just left with some impedances, the generator volt and the generator reflected by its voltage. So it has essentially become like the part A. We did exactly the same in part A, as you can see here. Let me just rub this out. Mhm. So if you see, now we have impedances. This is one impedance and this is my another impedance, or simply if you add these two impedances together, this is what you are gonna get. ठीक है जी? So far so good, students. Nice. Okay, so अब क्या करना चाहिए हमें? We can easily now find out the generator current. Okay, because now it's just like part A. So simply add these two impedances together, which we have done, and let's proceed further. So the generator current is simply now the total impedance, the total voltage, the generator voltage divided by the total impedance in my path. This is your generator current. ठीक है जी? So now we have find out. So since we have found out the generator current, it's now pretty easy to find out the remaining currents by simply using the relations for the current relationship for a transformer. We know how the primary and secondary currents are related for a transformer, and they are related with each other in terms of the turn ratio. So we are simply going to use those relationships, and then shall have the values of our line current and the load current. So let's begin with transformer T1, and we shall be working back through transformer T1. So we shall be applying the current relationship between the primary and secondary on the transformer T1, so that we can find out the line current, because we already have the generator current. Students, if you remember, on the primary side of the transformer T1, you had your generator current, and on the secondary, you had your line. So since I have the generator current with me, I can find out the value of my line current. Let's do it. Okay. Again, this has been shown here as well. Okay, so now this is your generator current, you know it. You need to find out the line current. We are going to use this transformer. There it is. So once we do this, we shall have a line current. Okay, so these are the relationships between the primary and secondary of a transformer. And since we do have the value of the turns ratio for this transformer, we can simply find out the line current. This is find out to be 9.594 angle minus 36.88 degree amps. So now once you have your line current, now the load current is also can be found out using the same concept. Let's do it. So again, as I said, that it's exactly the same procedure. What we shall work back through transformer T2. Okay, so at this moment we are considering this transformer only. Okay, this transformer, we have the line current, we need to find out the load current. They are related using the same relationships. Okay, then again, it's pretty straightforward, and you shall have your load current. Here it is, you have your load current with you, and now what's next, students? We just need to find out the load voltage, and again, it's simply the product of the load current and the load impedance. You now have the load current with you. Simply multiply it with your load impedance to find out the value of the load voltage. Let's do it. Yeah, it's pretty straightforward. Finding out the load voltage, you have your load voltage here. It's simply the product of the load current and the load impedance, and you get your required value. So now the very important part, the next part is finding out the transmission line losses. So the relationship won't change. It's the same as given by the square of the line current multiplied with the resistance in the line. Let's see what answer do we get. Okay, interestingly, this is your answer. If you do not remember the value, it was something like 1487 in part A. Now you see that the line losses have significantly reduced. This is the point which we were making initially. That why should we use transformers, and what is the significance of using transformers in your transmission system? See, the line losses have significantly reduced. So with this, we are done with part B as well. Let's summarize the findings. So the very important finding was that the transmission line losses, they reduced significantly, actually by a factor of 90, and this factor is huge. Reducing the transmission losses by 90 uh, is actually a significant contribution, but this doesn't make sense here because we are actually comparing it with a system in which there were no transformers at all. So just this was an example to show that why we need transformers. And do you did you get why the transmission losses, they reduce significantly? Yeah, it did reduce because of the use of transformer. But what actually happened? If you remember, we had transformer T1, which was a step up transformer. So what we did was we were transmitting at very higher voltages, 10 times more compared to the previous case. And you saw that the transmission losses, they reduced significantly. Apart from that, the voltage at the load also dropped less in the system with transformers, okay, as compared to the system without transformer. So in a nutshell, this is the summary. We saw this example actually illustrated the advantages of using higher voltages transmission lines. Because we use transformer T1, we stepped up the voltage when we were transmitting up, and also we saw the importance of transformer in modern power system. Okay, so that's all about this example, and I hope this is now clear to you. Inshallah, from next class we shall continue with some more new topics. So that's it for today, students. Thank you so much for being with me. I hope you were able to understand the concepts which we discussed today. If you still have any queries, feel free to write down me an email, and inshallah, I will reply your questions, your queries during our interactive session. Thank you so much. I see you inshallah in our next video. Thank you.